All right, everyone, settle in. Today we're going to pull back the curtain on a piece of tech you use every single day, probably without even thinking about it. We're talking about that journey electricity takes, from the socket in your wall, through that little power brick, and right into your phone's screen. And at the very heart of that whole process, there's a crucial little component we're going to get to know: the rectifier.
So, let's start with something you've all seen. You know, your phone charger, your laptop adapter, they all have that little blocky part, right? The brick. Why? Why can't we just have a simple cable that goes from the wall straight into our gadgets? Well, that question is the key to everything we're going to talk about today. So here's our game plan. First, we'll tackle the core issue, the AC-DC problem. Then, we'll introduce the hero of our story, the diode. After that, we'll look at a simple but kind of flawed first attempt called the half-wave rectifier, and then see how we can do much better with a full-wave rectifier. Finally, we'll get into the stuff you really need for your exams, with a side-by-side comparison, and then we'll wrap it all up. Sound good? Let's dive in.
Okay, first things first. To really get why that little charging brick is so important, we have to understand this: fundamental conflict. It's kind of like a tale of two very, very different types of electrical current.
On one hand, you've got alternating current, or AC. This is what's coming out of every socket in the wall. Think of it like a wave in the ocean, constantly flowing back and forth, changing its direction dozens of times every second. Now, this is great for sending power over huge distances from the power plant to your home. But your electronics, your phone, your laptop, they run on direct current, or DC. And DC is totally different. It's a steady, reliable, one-way flow of power. So you see the problem, right? Our gadgets need this calm, steady DC, but the wall is giving us this wild, weighty AC. That's the puzzle a rectifier has to solve.
So how in the world do we fix this mismatch? Well, we need a special component that can basically act like a traffic cop for electricity. And that brings us to the hero of our story, the humble PN junction diode.
So what is a diode? The easiest way to think about it is like a one-way street, or maybe an electronic bouncer at a club. It has one very simple, very strict rule. Electricity is allowed to flow through it in one direction. We call that forward bias, but if it tries to flow the opposite way, nope, the door is shut. That's reverse bias. It's an electrical gatekeeper, plain and simple.
And this right here shows you exactly what happens when we send our AC signal through this one-way gate. See the input wave on the left? It goes up into positive and down into negative. But the diode, our rectifier, it only lets the positive part through. The entire negative part of the wave, it just gets blocked. It can't pass. This is our first huge step in taming that AC current.
Now that we've got our magic component, let's actually put it to work. We're going to build our very first super simple circuit. You can think of this as our rough draft for solving the whole AC-DC problem.
And here it is, the half-wave rectifier. It's about as simple as it gets, really. You've got your AC source, a transformer to adjust the voltage, our hero component, just that one single diode, and the load, which is just representing whatever device we're trying to power. See? Super simple.
So let's look at the before and after. We start with our full AC wave, right? The output shows the diode did its job. It completely chopped off that negative half. So great. We've turned AC into what we call pulsating DC. It's not smooth yet, but at least it's only going in one direction. But do you see the huge problem here? We've just thrown away half of the power from the wall. That's incredibly wasteful.
And just how wasteful is it? Well, the absolute maximum theoretical efficiency you can get from a halfway rectifier is only 40.6%. Now, for your exams, you absolutely have to remember that number, 40.6%. It's a big deal. It basically means for every bit of power we pull from the wall, we're just throwing away almost 60% of it. That's not good. We can definitely do better.
Yeah, just blocking half the power isn't a real solution. It's a hack. We need a much more clever way to use the entire AC wave. And that brings us to a much more elegant design: the full wave rectifier.
Okay, let's put on our engineering hats for a second. The problem is that we're wasting that whole negative part of the wave. But what if instead of just blocking it, we could somehow grab it, flip it upside down, and make it positive too? If we could pull that off, we'd be using all the power the wall is giving us.
And that is exactly what the bridge rectifier does. Now, I know it looks a little more complex, but the idea behind it is absolutely ingenious. Instead of one diode, we use 4 of them, arranged in this special bridge or diamond shape. This clever setup acts like a really smart traffic controller, making sure the current always flows through our device in the same direction.
So let's follow the path.
During the positive part of the AC cycle, the current flows through this top right diode, D1, then down through our load, and back to the source through the bottom left one, D2. The other two diodes? They're just sitting there, turned off. The key thing is to notice the direction of the current through our load. But here's the brilliant part. When the AC source flips and goes negative, the current gets rerouted. Now it flows through the other pair of diodes, D3 and D4. But look, it still goes down through our load in the exact same direction before returning. Did you catch that? It doesn't matter if the input is positive or negative, the current going to our device is always flowing in the same direction. We've captured and flipped that negative half. It's just a beautiful piece of engineering.
Okay, class, time to really focus in. If there is one slide you need to burn into your memory for your exams, this next one is it. Think of this as the official report card, the ultimate cheat sheet for comparing these rectifiers.
This table really says it all. Let's look at the key differences. Diodes, 1 for half wave, 4 for the bridge. But now for the most important number on here, max efficiency. The half wave is stuck at a pretty terrible 40.6%. But the full-wave bridge rectifier jumps all the way up to 81.2%. That's literally double the efficiency. Also, look at the ripple factor. That's just a measure of how bumpy the output is. A lower number is better, and you can see the full wave is way, way smoother. This is the data you need to know.
And to make it even more obvious, this bar chart tells the whole story. The jump in efficiency is just massive. We go from wasting most of the power to actually using over 80% of it. This right here is exactly why pretty much every charger you own uses a full-wave bridge rectifier.
All right, let's bring it all home. Time for a quick recap of everything we've covered. What are the big ideas you need to walk away with from this explainer?
First, the problem. Our gadgets need smooth, one-way DC, but our walls give us wavy, two-way AC. The hero of the story is the PN diode, which acts like that critical one-way gate. Our first try, the half-wave rectifier, it used one diode but was super inefficient at 40.6% and wasted half the power. The much better solution, the full-wave bridge, uses 4 diodes to cleverly grab the whole wave, doubling the efficiency to 81.2%. And the result of all this? We've successfully turned that AC into a one-way but still bumpy, pulsating DC.
So we've made some amazing progress, right? We've gone from a wild wave to a bumpy, one-directional road. But we're not quite there yet. Your phone, it can't run on bumpy power. It needs a perfectly smooth, flat line of voltage. So the final question we have to ask is this: how do we get rid of those bumps and finally create that pure, clean power our gadgets need? Well, that's a topic for our next lecture. Class dismissed.